Hello guys, it's JohnnyTime and welcome to another smart contract hacking tutorial. Today we're gonna solve the fourth challenge in Damn Vulnerable DeFi side entrance. This is the fourth video in the series, and if you would like to watch the other solution, check out my playlist on my YouTube channel. And of course, if you enjoy this content, make sure to subscribe to get exposed to more awesome smart contract hacking and auditing related videos. Now without further ado, let's get started. So the fourth challenge is called Side Entrance. A surprisingly simple pool allows anyone to deposit ETH and withdraw it at any point in time. It has 1000 ETH in balance already, and it's offering free flash loans using the deposited ETH to promote their system. Starting with 1 ETH in balance, pass the challenge by taking all the ETH from the pool. Okay, so the first thing I want to do is jump into the smart contract and see what is this exercise is about. So I'm going to the contracts folder, and then we have side entrance and we have side entrance lender pool. Now this is the pool that was discussed in the description. We can see that because it's Damn Vulnerable version 3, we don't use Open Zeppelin contracts, but it was upgraded to use Solidity contracts. We have an interface of iFlashLoan Ether receiver, and we need to implement this execute function, which is a payable function that will receive probably ETH. Now, this is the side entrance pool. As we can see, we have a mapping that keeps tracks of balances. It maps between address to uint256. We have a predefined error, repay failed, and 2 events for deposit and withdraw. This smart contract does not have a constructor, and apart from the balances mapping, it doesn't have any other state variables. Well, it has 3 functions: deposit, withdraw, and flash loan. Deposit is a payable function that receives ETH and simply just add the ETH to the balances mapping for the message sender and emits a deposit event. Now we use the unchecked block over here because we want to save some gas, because there is no chance for overflow or underflow, and we can use this unchecked to avoid the built-in underflow and overflow check that exists on Solidity versions 0.8 onwards. Now, regarding the withdraw function, we first take the current amount that the user has from the balances mapping. Then we delete the record for the balances for the user, which means that the user is going to have 0 in balance because we deleted the key in the mapping, so the value basically. We emit an event, and then we use the safe transfer lib by Solidity in order to transfer the ETH. We use the safe transfer ETH to transfer it to the message sender, and this is going to be the amount that he owns. So he cannot withdraw only partial of his amount, but if he withdraws, it's all the amount at once. Now, this is the function that they discussed in order to promote the protocol. They offer flash loans for free, so anyone can call this function and request an amount. We first check the contract balance, so we check the ETH balance of this pool smart contract. Then we make the callback to the receiver. The receiver is the message sender, the one who called the flash loan function. We call the execute function that need to be implemented in the receiver, and we send the ETH as the value, the amount that he requested. So we just give him the ETH, but we make sure at the end of the transaction that he paid back the ETH. How do we check that? We check that the balance, if the balance of this smart contract after we send him the ETH and we issued the callback, after the balance that we have after should be not lower than the balance that we have before. So we can either have the same balance or greater. If it's lower, then we're going to revert with repay failed. So this is pretty simple, not much functionality. We have only 48 lines of code here. Some of it is even comments. Really very simple smart contract, but we need to find a way to steal the money from this pool. Now, before we try to think how to exploit it, we need to take a look at the test file to understand how the state look like and see how it's being implemented. So as we can see, we have the Ether in pool, which is 1000 Ether like was described in the description of the exercise. We have only 1 ETH in balance, as you can see over here. And we have 2 accounts in this scenario. We have deployer and player. Here we deploy the pool from the deployer account and we deposit the Ether in pool from the deployer. So we deposit this 1000 ETH in the pool, like it was described in the exercise. Then we make sure that the balance is 1000 ETH. We use the set balance helper function from the Hardhat network helpers in order to set the player balance to 1 ETH, because by default, all the accounts that we get from Hardhat, they have more. I think they have 10,000 ETH. So we make sure that the player has only 1 ETH and we validate it. Now, this is our malicious code section. This is where we have to implement our exploit to get this desired state. And the desired state is that the pool address will have 0 ETH in balance and the player address should be greater than the Ether that we have in pool, which means greater than 1000 ETH. Now, going back to the contract and trying to find the vulnerability, it seems like the functionality is super simple and the functions themselves are not vulnerable to any common known vulnerabilities such as reentrancy or like arithmetic overflows, if you're familiar with these vulnerabilities in Solidity, because here we don't do much rather than updating the balances. Here we first update the state and then we make the external call and transfer the ETH. So we follow the check-effects interactions, and also here in the flash loan, we make sure that the payment was paid back. So we cannot steal money by using the flash loan, because if we will not pay back the money, the transaction will be reverted. So it's a bit tricky and we don't really know how to approach this exercise and how we can activate our attacker mindset and which function we can exploit in order to steal the funds. Now that's where we need to activate our creativity and our attacker mindset. We need maybe to exploit multiple functions all at once in order to manipulate the state of the smart contract. Now think about it that way. How you can use multiple functions in this particular contract in order to manipulate the state to something that the developer of this pool smart contract did not expect and something that he did not think of. I want you to pause this video, take a look at these 3 functions and try to see how you can make some kind of cross-function exploit. Now, if you find it a bit challenging to activate this attacker mindset and you feel that you need some stronger foundation in order to solve those damn vulnerable DeFi exercises, feel free to check out the complete fundamental smart contract hacking course. This is a course that I have created to give you the right skills to get started with smart contract hacking and auditing with huge syllabus, right? And every chapter that we're gonna cover, it comes with exercises and walkthroughs, like exactly like the one that we have this one, but it's gonna be a very structured path in order to become a hacker and an auditor. So you're gonna learn all these kind of attacks and simple and advanced attacks. And right after every chapter, it will be taught either by me or guest lecturers, professional from the industry. You're gonna practice what you learned through scenarios and exercises and hacking and fixing smart contract. Now, another cool thing is that you'll be able to join an awesome exclusive Discord community with more students and the rest of the teachers in the course, so you can learn together with other people and connect with people from the industry. And of course, in the end of the course, you will have a final exam. When you finish this final exam, you will get a certificate that will help you to prove and showcase your skills and obviously increase your chances of getting your first smart contract auditor position. So if you're interested, check out the special link in the description below to get a limited time discount and get everything that I described with a very nice good discount and a good price. Now, going back to the exercise, I want you to imagine this scenario. Let's say we take a flash loan from the smart contract. So we request a flash loan, let's say the whole balance of the pool. We request 1000 ETH flash loan. We pass here the 1000 ETH in decimal numbers parameter. Now we're gonna get the money, right? This execute function will be executed in our smart contract, but we cannot keep it, because if we keep it, basically what will happen is this line of code will be executed and the whole transaction will be reverted. So what we can do with this money, so this if statement will not be satisfied, it will not be executed and it will not be reverted, but we will be able to take the money later on. So we're gonna leave some kind of backdoor similar a bit to the previous exercise, but different kind of backdoor. So what we're gonna do in that case, we're gonna simply, once we get the funds here in this line of code, the execution moves to our external malicious smart contract. Now in this malicious smart contract, instead of keeping the funds to ourselves, we're gonna send back the funds to the contract. But instead of just sending it back, we're gonna send it back through the deposit function, right? The deposit function is payable function, so we can simply call the deposit function with the ETH that we received from the flash loan. Now the balances mapping will be updated with this amount, which means that we basically let the contract think that we own this 1000 ETH, we deposited it, right? So we update the balances mapping with ETH that we actually do not own, but we own for a fraction of a moment during the flash loan. Now let's imagine what happens after we do it, after we deposit it through the deposit function, after we got the money in the flash loan. So the outcome will be that the balances mapping will be updated with this amount. So the contract owns us 1000 ETH, but the balance of the contract will still be the same because we paid back the ETH, but instead of just paying it back through a receive function, basic default fallback or receive function, we paid back through going through the deposit function, and we made the contract think that we deposited this ETH and we own this ETH even though we don't own it because we just got it through a flash loan. So this is a genius cross function attack. Very simple, very creative, but once we do it, we can fool the state, and it just shows the importance of looking at the contract as a whole and not on every single function and fix the vulnerability for single function, but look at the state of the whole contract and how we can do cross-function or sometimes even cross-contract exploitation. Now, we will have to implement our malicious smart contract because in order to receive the flash loan, we need to create a smart contract that implements the execute function. So the first thing I'm going to do is go here to side entrance and to player contracts. And what I'm going to do, I'm going to create a new file. I'm going to call it attack side entrance.sol. So this will be our malicious smart contract. I'm going to copy just this for a template. I'm going to remove here the safe transfer lib. And I'm probably gonna remove all this functionality because I'm not gonna need it. I just want some kind of template to get started with. And we can remove also this one. And let's call it attack side entrance. So first I'm gonna remove also this interface. Basically, I didn't need to copy it, but I don't know, I'm just lazy. So first thing I'm gonna do is write the interface of the pool interface because we're gonna interact with the pool through this smart contract. So interface I pool, and we will implement the different functions that we want to use later, okay? Let's start with the state variables that we need. We're gonna interact with the pool smart contract in this smart contract. So we'll define here I pool, immutable, and then pool. I'm also gonna eventually, after we steal the money from the pool, I'm gonna send it to the EOA account because in the end, we have this check that makes sure that the player EOA account has the ETH and not the malicious contract. So I will save it as a state variable. So it will be address immutable, and I will call it player, right? Now here, why do we have an error? Attack set error, blah, 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 blah. Okay, because we didn't initialize immutable variables. So we're gonna initialize them with the constructor. And in the constructor, we're gonna receive two parameters. First, it will be address pool, the address of the pool, and address of the player account. Now we can set those state variables. So I'll do something like pool equals iPool, and I will pass here the pool address. I don't need to pass the player address. I don't know why it auto-corrected me to do that. And the player is just simply gonna be the player that we passed through the parameter. Now we want to start and implement our attack function, the function that will start and initiate the exploit and the attack. So it will be function, attack, and it will be external function. Now we don't need to implement we don't need to receive any parameters because we already have the parameters here that we said, the pool and the player address. But first, we're gonna do some, you know what? We don't need to do the required statements over here. We'll do them later. You will see in a moment why. But the first thing that we need to do to initiate the attack is request the flash loan. So we need to call the flash loan function. That's why I'm gonna copy here for our interface, the flash loan function here. And I will change it to a semicolon. This is our interface. And now we can just call it from our malicious contract. So I'll do pool.flashloan, and we need to pass the amount. Now, what is the amount that we want to request flash loan? We want the whole ETH that we have in the pool. So I will do address pool.balance, right? We're requesting all the ETH that we have currently in the pool contract, and we're requesting it for a flash loan. Now, once we request the flash loan, we have to remember that this line of code will be executed, and this line of code will be executed, which means that the pool contract will call our smart contract. So in order to receive this call, we need to implement the function execute, and it will be again an external function, and it should be also a payable function, right? Because this function should receive ETH. So it will be an execute and it will receive ETH. It doesn't get any parameters. Now in this function, we need to pay back the ETH to the pool smart contract, and we're gonna do it through the deposit function. But before we do so, let's make some access control happen over here. We want to make sure that the message sender, the one who started this whole thing, the TX origin, let's start with the TX origin. The one who sent the original transaction, the EO account who sent the original transaction is the player. So no one else can basically use this smart contract, only us, the malicious attacker. And we require also that the message sender, which means the one who called this function, is gonna be the address of the pool smart contract. So no one can call this function apart from the pool, and no one can initiate a transaction that eventually will come to the execute function if it's not the player. So we have this access control to make sure that only our attacker account can trigger and initiate this attack functionality. And now that we made this access control at our OPSEC, we're gonna call the pool.deposit. But before we do so, we need to implement the interface. So I'm gonna again copy it from the pool, here change it to semicolon, now that we have the deposit function, and we're gonna call the pool.deposit function without parameters, but with value. So the value that we're gonna send is gonna be the message.value, or in other words, all the ETH that we received from the flash loan, because this is gonna be in the message value, right? So we deposited the money in the pool. The contract is happy because the balance is not lower than the balance that it had before. And now here, once we finish the flash loan, which means that this line was executed already and we passed it, this is the time to withdraw the money that the pool think that we have, even though we don't, because we just borrow it for a fraction of a moment to deposit it, so it will think that we have it. So we're gonna do pool.withdraw. Now let's copy again the interface. So we have the interface over here, and withdraw, we just call it as is. We don't need to pass any parameters. Now that we withdrew the money, we need to receive it to the contract. So it's very important to remember to add this receive default external payable fallback function payable. So without implementing this function, basically we won't be able to receive ETH in the contract once we get it through the withdrawal function. So if you forget to implement it, don't be surprised that your exploit will not work. Now, after we ran this withdraw function, simply we receive the ETH, and then we can just send it right to the EOA account, to the player account. So we're gonna do something like bool success, and we don't need a data parameter. So we're just gonna do player.call. We are making an external call to the player with the value will be the message value. So it's all the ETH that we got from the withdraw function. And this will be just, you know what, let's make it just more safe. So I'll do address this dot balance. So we basically gonna send all the balance that we have in this attacker smart contract directly to the player, to the attacker EO account, to the MetaMask account, whatever, you name it. Now that we have all the functionality implemented, the attack function, the execute callback function, the receive fallback function, everything is set, looks good. It's time to deploy the smart contract in the script. So we go back to the JavaScript file, and this is the time to deploy the contract and run the exploit. So this .attacker contract equals await, and we're just gonna use the factory. So it will be another await here, and iter's.get contract factory. Now the contract name is gonna be attack side entrance, right? And we're gonna use the player account to deploy it, right? So we're using the player account to deploy it. Let's just close this bar over here, and we will call the deploy function. Now, the deploy function needs to come with two parameters, right? The first parameter should be the pool address. The second one should be the player address. So we have the pool over here. So it will be address, I think with JavaScript, it's pool.address. And this one will be the player.address. So we pass these two parameters to the constructor of our attacker smart contract. And now all there is left to do is just to initiate the attack. So we'll do await this.attacker contract.attack. So we call the attack from the player account. Now, you know what? Let's just do .connect player just to make sure that we call it. No, actually we don't need to do so because we deploy this contract with player. So by default, we're going to send transactions from player. So it's not necessary. So this should be enough, guys. We deploy the malicious contract. We call the attack function to initiate the whole attack, the whole functionality that we just implemented. And if we're lucky enough, we should achieve this state where we have all the ETH in pool. So this is the money time, guys. It's time to run the exploit and see if we succeeded. So yarn side entrance and trends, and let's cross our fingers over here. And congratulations, guys, you completed the 4th Damn Vulnerable DeFi challenge. It wasn't easy. I hope that you learned a lot from this challenge, and if you have any questions, make sure to ask them in the comments below. If you like it, please smash the like button and subscribe to the channel for more awesome videos in the future. Thank you so much, and I will see you in the next one. Bye bye.